There are things that take lives so slowly that a person can live an entire life, win 2 Nobel Prizes, change science forever, and only then die from the very thing they worked with. And then there are things that kill young women in a New Jersey factory, while their employers know the truth and remain silent. And then there are things that indigenous peoples on the shores of Great Bear Lake in Canada, while the whole world applauds progress. Incidentally, these are the same substance. Element number 88 on the periodic table. Friends, welcome to the Fool's Gold channel, a channel where we take the periodic table and find stories you definitely didn't expect to find there. Today it's radium, and by the end of this video you'll likely look at the luminous hands of an old clock in a completely different way. So let's start with a detail that's often overlooked. The National Library of France in Paris houses an old notebook. Leather cover, yellowed pages, handwritten notes. An ordinary object from the era, but you can't pick it up. You physically can't. The library won't let you. Just getting close to it requires protective suit and special permission from the library administration, because this notebook is still radioactive. 90 years after its owner's death, it continues to emit radiation and will continue to do so for another half-century. Such is the nature of the element that permeated its pages. It was Marie Curie's workbook. I think many have guessed. She held it in her hands every day, wrote notes, put it away in a drawer, and took it out again, and so on for years, while the element she discovered slowly did its work. That's where we begin. Not with a table, not with a formula, with a woman who didn't know she was killing herself, or knew and continued working anyway. 1897, Paris. Marie Sklodowska-Curie is looking for a topic for her doctoral dissertation. This in itself is a story, because women with doctorates in Europe were practically non-existent at the time. Maria was an exception, fighting her way up the ladder at every turn. But that's not the point now. The topic she chooses is the mysterious radiation of uranium discovered a year earlier by the French physicist Henri Becquerel. Becquerel noticed it by chance. Uranium salts blew out a photographic plate, even through several layers of black paper, even in complete darkness, without light, without an obvious energy source. Becquerel recorded the fact and essentially stopped. Maria asked why. She began systematically measuring the radiation intensity of various uranium compounds. They use an electrometer, a device that allows for the precise recording of the electric current that occurs when radiation ionizes the air. An important detail. From the very beginning, she works with numbers, not simply observing phenomena, and discovers something strange. Uraninite, a rock containing uranium, is also called pitchblende, the hero of one of our previous episodes, by the way, radiates significantly more actively than pure uranium, so much so that the difference can be explained by the uranium content of the rock alone. Her conclusion is straightforward and bold. There's something else in the ore, an unknown element, or even several. Something no one has ever seen. Maria introduces a word she coined herself: radioactivity. Before her, the term didn't exist. The phenomenon itself existed. Becquerel discovered it. But Maria turned a chance observation into a scientific subject, a measurable, reproducible, and studyable phenomenon. Now she needs to find that unknown. Tons of ore. Chemical separation without any automation, by hand, in a room that Maria herself called a barn. Because it literally was a barn. Former outbuilding at the Paris School of Medicine. Earthen floor, leaky roof. It was bad heated in winter, and scorching hot in summer. No ventilation. This last fact about ventilation will prove important a little later. Marie and Pierre Curie brought several tons of uranite there from Jagomov, a Bohemian town in what is now the Czech Republic. The Austrian government gave away the waste from uranium mining for glass making, practically for free. Who needs waste? French scientists did. They began separating, dissolving in acids, precipitating, filtering, calcining, dissolving again, searching for the fractions with the highest radioactivity, and continuing to purify them. After several months of work, in July 1898, by the first result, a new element, Marie calls it Polonia, after Poland, which didn't exist on the map at the time. It was divided between the Russian, German, and Austro-Hungarian empires. The chemical name as a political gesture, encrypted. But something else remained. Even after the isolation of polonium, the activity of the work was not fully explained. So there was another element there. December of the same year, a second element. Maria suggested calling it radium, from the Latin word for radius meaning ray, because it glowed. Concentrated, radium preparations literally gave off a faint bluish glow in the dark. The radiation excites air molecules around the source, causing them to emit a faint light. The discovery itself was announced, but chemists demanded proof of a different kind. They needed to isolate a pure substance in sufficient quantity to determine its atomic weight, otherwise it would just be empty words. This took another 4 years. 4 years of working with tons of ore to ultimately obtain about 1 gram of radium chloride. Enough to accurately determine its atomic weight, enough that no one could ever doubt the existence of the new element. In 1903, the Nobel Prize in Physics was awarded. Maria, Pierre, and Becker received it jointly for their research on radioactivity. Here it's worth mentioning one decision Maria made during this period, one that cost her and Pierre enormous sums of money, deliberately. When the method for chemically isolating radium from uranites became viable, industrialists began approaching them with an obvious proposition: patent the process. This is standard practice. It's money. Big money. Demand for radium in medicine and industry was already looming. Maria and Pierre refused. They published a full description of the method in an open scientific journal, free of charge. Maria's explanation was simple. Scientific knowledge belongs to humanity, not to individuals or companies. Frankly, I respect such tenacity. It's just a shame that this decision didn't pay off. This choice had direct consequences. American and European companies immediately used the published method to create their own radium production facilities. An entire industrial sector emerged, without any royalties from the discoverer. Maria struggled financially to finance her laboratory for the rest of her life. She literally had to beg governments, philanthropists, and American universities for research funding. One of the richest topics in the history of industrial chemistry, and its discoverer received nothing from it. When American journalists asked her what she dreamed of in the 1920s, Maria would answer, 1 gram of radium for research. Because she couldn't buy it with her own money, it cost about $100,000. American women held a public fundraiser and bought the gram. It was ceremoniously presented to her at the White House in 1921 in the presence of President Loren Harding. The woman who gave the world a method for producing radium received 1 gram of this very radium as a gift from American housewives. In 1906, Ie died under the wheels of a loaded carriage on Paris Street. A slippery accident. Maria was left alone with 2 daughters and a laboratory. She continued her work, heading Pierre's department at the Sorbonne, first female professor in the history of this university. In 1910, together with colleague André Louis Bjorn, you first obtained pure metallic radium using electrolysis with a mercury cathode. In 1911, she won her second Nobel Prize in chemistry. The first person in history to win 2 Nobel Prizes, and still the only woman. And all this time there was the shed, solutions, acids, radioactive substances in bare hands. Radon, which was constantly released from radium and accumulated in an unventilated room. No dosimeter, no protective suit. The concept of an acceptable radiation dose didn't exist in 1900. It simply wasn't in the dictionary. Marie Curie was almost blind by her 30s. She had cataracts in both eyes. She underwent surgery several times under different names to avoid being recognized by the press. Her fingers were rough and cracked from years of working with chemical reagents. Chronic fatigue, which she attributed to her age and the volume of work, was plaguing her. Blood tests showed increasingly alarming indicators. She continued to lecture. Continued to direct the Radium Institute in Paris, which she herself had founded. She continued to communicate with physicists around the world. In July 1934, she died of plastic anemia. Bone marrow stops producing blood cells. This is exactly what radium does, accumulating in bones. It destroys the tissue responsible for blood. She was buried in the cemetery next to Pierre. In 1995, their remains were transferred to the Pantheon, the National Memorial of France. The coffin was placed in a lead case because her remains are still radioactive. Consider this detail. The woman died over 90 years ago, and her body still requires radiation protection for reburial. A lead coffin in the Pantheon. A lead container with a notebook in the National Library. The same story told twice in that notebook is still there. Radium-226 deposited to the pages over the years of work has a half-life of 1,600 years. After 1,600 years, it will remain there for half that amount. The book will continue to emit radiation for several more millennia. Civilizations will rise and fall, but this notebook will still be playing around silently in a lead box. And finally, a detail that seems to me the most telling in this entire family story. Maria had 2 daughters. Irene, the eldest, followed in her mother's footsteps, became a physicist and chemist, and won her own Nobel Prize. She died at 58 from leukemia, the consequences of radiation. Same story, second generation. Eva, the youngest, did not become a scientist, but became a journalist and pianist. She wrote her mother's biography, which has been translated into several dozen languages. She married an American diplomat. She lived to be 102. The only one in the family who did not work with radioactive materials. The only one who lived to be 102. It's not a moral, it's just a fact. I think after the story, it's high time to figure out why radium even exists on Earth. There's a fact that surprises many. I've even seen comments on this topic under other videos. If this element is constantly decaying, why hasn't it become zero over the billions of years the planet has existed? Because it's being produced, right now, continuously, under our feet. But to understand the full picture, we need to go even further, not underground, but into space. And not millions of years ago, but billions. Uranus itself, from which radium is born, didn't appear on Earth because it originated here. It was baked into the planet's matter during its formation about 4.5 billion years ago, and before that, it was synthesized in the depths of massive stars and at the moment of their death in supernova explosions and in neutron star collisions in. It is these catastrophic events that provide enough energy to create heavy elements, uranium, thorium, and everything heavier than iron. The gas-filled cloud from which our sun and planets later formed already contained this uranium. Earth inherited it at birth. So the radium that is being formed right now in the granite beneath the foundation of your house is a distant echo of the stellar catastrophes that occurred before the solar system formed. Simply a very slow echo, stretched out over billions of years. Uranium-238 is one of the longest-lived radioactive elements on Earth. Its half-life is comparable to the age of the planet itself. It slowly decays in a chain of 14 intermediate steps. During one of these steps, radium-226 is formed. As long as there is uranium in the Earth's crust, there's radium. They are inseparable. This is precisely why the uranium I ate from Yakimov turned out to be so active. For millions of years, the uranium in this rock produced radium, which then accumulated there. On average, granite contains about 1 gigagram of radium per 3 million tons of rock. This explains why the Curies needed several tons of high-grade ore and 4 years of work to obtain 1 gram. As radium decays, it emits an alpha particle, a helium nucleus, and turns into radon. The gas is invisible, odorless, and also radioactive. It simply disappears into the air. In that Parisian barn on Rue Colmenard, It went straight into the lungs of Marie and Pierre, because there was no ventilation. An alpha particle is practically harmless outside the body, lingering on the skin, but inside the body, in the lungs or bones, it releases all its energy literally on the spot. The density of cellular damage is colossal. And here's the key. Radium behaves chemically like calcium. The body cannot distinguish between the two. Once in the blood, radium goes where calcium would go, into bone tissue. There it settles and continues to work right in the bone marrow where blood is produced. Remember this fact. It will explain several subsequent stories at once. Through Radi, humanity first learned the true age of the Earth. This sounds surprising, but it's a fact. At the very beginning of the 20th century, people didn't know how old the Earth was. Biblical calculations gave it around 6,000 years. Physicist William Thomson, known as Lord Kelvin, based on the rate of planetary cooling, estimated it at 20 to 100 million years. Geologists suspected it was longer, because sedimentary rocks accumulated too slowly for such figures. But there was no proof. Between 1901 and 1905, Ernest Rutherford, an American chemist, Bertrand Boltwood, developed the first radiometric dating method for rocks using the ratio of radium to its final decay product, lead. The logic was simple. If you know the decay rate and measure the ratio of the original substance to the final one, you can determine the age of the sample. In 1907, Boltwood published his first results. The ages of several uranium minerals ranged from 400 to 2,200 million years. These figures shocked the scientific world. The Earth turned out to be incomparably older than anyone thought. Lord Kelvin, who was 83 at the time, refused to accept these results for the rest of his life. But science didn't question him. It was through radium, through measuring its content and the content of its decay products in rocks, that humanity first obtained the true estimate of the Earth's age, 4,500,000,000 years. The figure that every school child knows today arose from work with this element. In 1910, the International Scientific Commission established a unit of radioactivity, the Curie, named after Pierre Curie. 1 Curie unit is equal to the activity of 1 gram of radium-226 lux. In other words, radium was chosen as the reference point for measuring the radioactivity of everything from medical isotopes to nuclear reactors. Nowadays, the becquerel unit is more commonly used in scientific calculations, but historically, it was the first standard. Now let's move on to money. Big money, and how one element became the subject of an international industrial war. By the 1920s, radio production had become a serious business. Medical applications were growing. Luminous dials were produced by the millions. Industrial radiography was gaining momentum. 1 geometer of radium cost around $100,000, and demand was only growing. Uranium ore remained the primary source of raw material. After the discovery of Chinkoloblo, the richest uranium deposit known at the time, in the Belgian Congo in 1913, the Belgian company Union Mineria de Katatanga established a near monopoly over the world's uranium ore supplies. This gave Belgium, or more precisely, the Belgian colonial possessions, a huge geopolitical advantage. Ore processing in Rada was conducted primarily in Europe, in Belgium and France. The United States, which by this time had already established its own radium production based on uranium ores from Colorado, found itself at a disadvantage. Their ores were poorer. Competition raged on several levels simultaneously, for control of deposits, for processing technologies, for patents for medical applications. Several American companies in the 1920s attempted to establish cartel agreements with European producers to stabilize prices. Their success was mixed. Marie Curie, who made the method for isolating radium publicly available, watched all this from the sidelines, without royalties or profit sharing, with the unwavering conviction that she had done the right thing. 1935, Great Bear Lake, Northwest Territories, Canada. Eldorado Gold Mines is developing a uranium deposit. The mine is literally at the edge of the inhabited world, accessible only by air or water. The nearest settlement is that of the Dina Native Americans, who have lived here for millennia, hunting and fishing. The company hires them as porters. The task is simple. Load bags of uranium ore onto a barge and carry them along the shore where the barge can't get close. The bags are unmarked, without instructions, without any protective clothing. Men carry the bags of ore on their backs, clutching them to their bodies. Children sometimes play near the waste heaps. No one tells them what this material is or what it does to the body.
Decades later, the Day community is stricken with cancer.
One by one. Those who worked as porters in the 1930s and 1940s, or their sons who played near the ore. An official investigation only began in the 1980s when survivors and their relatives began seeking answers. The Canadian government conducted a study and acknowledged a link between work at the mine and cancer among Dennis porters. In 1998, the government issued an official apology to the Dean communities. An apology after 60 years. So what were they supposed to do with that apology? The question is, of course, rhetorical. The story of the Radium girls of New Jersey became famous. It went to court and changed the law. The story of Dennis's rapist from Big Bear Lake remained virtually unknown outside of Canada. No trial, no compensation comparable to the scale of what happened. Just an apology. The difference is in who exactly suffered and who had the resources to seek justice. Now, in more detail. 1917, Orange, New Jersey, at the United States Radium Corporation plants. Several hundred young women work here producing luminous dials for military watches. World War I is raging. The military needs watches that can be read at night, in the dark, in the trenches. A luminous dial is a direct military necessity. A radium-based graphene mixed with zinc sulfide glows in the dark without any external light source. It is the radium that irradiates the phosphor, causing it to glow continuously. The work was meticulous. You had to apply paint precisely along the outline of tiny numbers with a thin brush. The brush quickly lost its shape and frayed, so every worker was taught one technique: sharpen the brush in your mouth, place it between your lips, lightly moisten it with saliva, twirl it, and pull out the sharpened tip. This was called the lip method. It was taught officially as a work skill. Workers painted their nails, teeth, and faces with luminous paint before going on dates. It was fun. They glowed in the dark. Management looked on indulgently and said nothing because they knew something they were keeping quiet about. The company's own scientists worked with completely different precautions, using tongs and lead faucets. Medical journals had already published data on the health risks of radium. In 1925, Harvard industrial hygiene specialist Alice Hamilton bluntly described working conditions in radium factories as dangerous. The company continued operating and continued to tell complaining workers that their problems were personal. The first symptoms appeared in the early 1920s: toothaches, teeth that crumbled for no apparent reason, then jaw pain, then worse. When workers began seeking medical attention for unexplained bone loss in their jaws, the company found an explanation: syphilis. It was a cruel and calculated decision. In the 1920s, an accusation of syphilis completely destroyed a woman's reputation. Many fell silent, fearing the consequences more than anything else. But not all. In 1927, 5 former workers went to court. Their names were Gracia Fraher, Ed Hasman, Catherine Schaap, Alberto Laus, and Quinta McDonald. Their lawyer, Raymond Berry, took the case without pay. The women had no money. The company used every legal mechanism available to delay the process a la balis. Appeals, procedural objections, requests for continuances. The logic was simple: let the plaintiffs die before a decision was reached. Then the case would close. Catherine Schaap signed the agreement, but never had a chance to use it. She died in 1929, less than a year after signing it. The other 4 were brought to court on stretchers or in wheelchairs by the time of the final hearing. In 1928, the parties reached a settlement. Each of the surviving plaintiffs received a lump sum of $10,600 annually for life, plus 600 in medical bills. For what happened to their bodies? But a precedent had been set. This case became the first in American history where a court found an employer liable for an occupational disease caused by intentional concealment of information about a hazard. Before this, a corporation could claim anything it wanted, and workers had no means of proving otherwise. Afterward, a system began to emerge. The Radium girls are studied today in American law and medical schools. Their case directly influenced the development of labor laws regarding protection from occupational diseases. Here's a question for you, an honest one, not a rhetorical one. Had you heard of this story before today's video? Let me know in the comments. I'm genuinely curious. While women were dying in a New Jersey courtroom, something completely different was happening in Manchester. Ernest Rutherford, already a major scientist by 1909. A New Zealander by birth working in England, he had won the Nobel Prize in Chemistry the year before for his research into the nature of radioactivity. But he was truly preoccupied with another question. What is an atom, anyway? What's inside? The dominant model at the time was Thomson's. An atom is like a uniformly charged sphere with electrons embedded in it. Like a raisin, if you want a common analogy. A beautiful, logical picture. Only incorrect, but no one knew that yet. Rutherford takes thin gold foil, almost transparent, several thousand atoms thick, and bombards it. Bombards it with alpha particles. The source of alpha particles is radium. It is radium that provides them in the required quantity and with the required energy. Without a suitable radioactive source, the experiment would not have been possible. The logic is simple. If the atom is a uniform sphere, alpha particles should pass through the foil with slight deviations, like a bullet through soft clay. Slowing slightly, changing direction slightly. Most particles do just that, passing almost straight ahead, but a tiny fraction bounce back almost at an angle close to 180 degrees. Rutherford would later say it was like firing an artillery shell at tissue paper and having it bounce back and hit you. The conclusion that follows from this observation changes everything. The atom is almost empty. At the center is a tiny, incredibly dense nucleus. Around it are electrons spaced enormously apart by atomic standards. The void between them is more incomparable than the substance itself. That picture of an atom with a nucleus at the center that you've seen in textbooks was born in Manchester in 1911 from gold foil and radium alpha particles. Without radium, Rutherford would have had no source. Without a source, there is no experiment. Without an experiment, there is no nuclear physics as we know it today. While physicists were making discoveries, entrepreneurs were making money. And here begins the part of radium's history that is now remembered with a mixture of amazement and horror. By the 1910s, radium's fame had spread far beyond scientific journals. The mysterious element which glows on its own was associated with the name of a two-time Nobel laureate. That was the perfect marketing material, and the market responded with the imagination characteristic of the era. A French cosmetics brand released a face cream called Radio containing thorium and radium. It was marketed as a skin rejuvenator and sold in pharmacies. It was sold until the 1950s, after the harmful effects of chronic radiation exposure had become a medical consensus. Advertisements for this cream featured a portrait of a doctor in a white coat. Doramat toothpaste containing radium was produced in Germany. The packaging literally read, activates gum tissue. Radium-containing chocolate is neither a fiction nor an exaggeration. In Germany in the 1920s, a company produced chocolate candies under the name Choco Radium. Advertising promised a tonic effect. They were sold in pharmacies as a therapeutic food. In the United States, from 1918 to 1931, a product called Radium was sold. Distilled water with dissolved radium isotopes was positioned as a tonic and restorative. One buyer, American industrialist Eben Bayer, took Radium regularly for several years. In 1932, the Wall Street Journal published an article about its fate. The headline read, "Radium water worked great until his jaw dropped." This is a literal description of what happened to his bones. Radium, mimicking calcium, destroyed his skeletal structure from the inside. Byers died that same year. American entrepreneur William Bailey produced a device called the radiodocrinator, a small belt-shaped device containing radioactive material. It was intended to be worn on the body. Advertising materials explicitly stated its supposed restoration of male energy. It had been sold since the 1920s. Byers himself later died of bladder cancer. There was even radium bathwater, special porcelain vessels with a radioactive coating inside. They were sold in Germany and Austria as a home remedy for bathing. Advertising invoked the natural radioactive springs of Baden-Baden and Carlsbad and offered the same effect without leaving home. These are not isolated cases of eccentricity. It was an organized, packaged market with advertising budgets, distribution networks, and positive reviews from doctors in magazines. The 1920s in Europe and the United States can, without exaggeration, be called the era of radium craze. In advertising, the word radium was lumped together with words like health, youth, and energy. It was a brand, a working brand, because the link between chronic low-dose irradiation and cancer had not yet been proven with the necessary rigor. Acute radiation damage from powerful sources was already known. The long-term effects of moderate to chronic irradiation were not. And the market thrived in this gap. Incidentally, radium production is a story in itself, almost never told in its entirety. In the first years after its discovery, the main source was the Jeshimov Valley in Bohemia. But by the 1910s, it became clear that European reserves were limited and demand was growing. In 1913, geologists discovered the richest deposits of uranium in Katanga province, then part of the Belgian Congo. The Shinlubwe deposit contained uranium ore with a concentration many times higher than European sources. Mining began immediately. Working conditions in the mines offered no radiation protection. Congolese workers mined the highly radioactive ore with virtually no protective gear. For obvious reasons, no one kept medical records of the workers' health. Katanga ore was initially used for radium production in Europe and the United States. When World War II began and the race for nuclear weapons began in military programs, some of the uranium feedstock for the American Manhattan Project was mined in Shinlubwe. This is a documented fact confirmed by declassified archival materials. It is important to understand one thing that is often not explained. Radium was never mined as a standalone product. No wells were drilled for it, nor were separate mines built. It was always a byproduct, extracted from the waste after uranium ore processing using chemical precipitation methods. Initially, they took what they needed from the ore, uranium, and extracted radium from what was left. Today, the largest uranium producers are Kazakhstan, Canada, Australia, Namibia, and Uzbekistan. In recent years, Kazakhstan has accounted for approximately 40% of global uranium production, and it is during the processing of this uranium that radium is produced as a byproduct. Radium-223 for Safika is produced differently, artificially in nuclear reactors, by irradiating radium-226 with neutrons, Natural ore has no role here. As for the impact on the biosphere, the picture is inconvenient but true. Soils and water bodies near uranium production accumulate radioactive elements from tailings, ponds, and ore processing waste. Radium is washed out of these waste dumps by rainwater into groundwater and is absorbed by plants. In a number of areas near old uranium mines in Central Asia, Africa, and North America, elevated radium concentrations in drinking water and soil several times higher than background levels have been recorded. This isn't a global disaster, but it is a localized contamination that impacts the health of people living near such sites. At the same time, in the 1930s and 1940s, radioactive waste was used in industry in a field few remember today. Radiographic testing, the scanning of metal structures to detect internal defects, cracks, pores and imperfections in welds was used. How can you check for a crack inside a steel weld several centimeters thick without destroying the structure itself? Radium emitted gamma rays which passed through the metal and exposed the photographic film from the other side. The effects were visible as shadows in the photograph. Radium sources for industrial radiography were used in shipyards, aircraft factories, and bridge construction. They were handled far less carefully than would have been desirable. Workers lacked dosimeters, storage procedures were minimal, and source inventory was perfunctory. After the war, radium was replaced in industrial radiography by Iridium-192 and Cobalt-60, more convenient and less expensive gamma radiation sources. But the old radium sources remained. Many ended up in basement storage rooms and warehouses without proper inventory. This problem of abandoned industrial and medical radium sources has still not been fully resolved. Here's another story. 1987, Guyana, Brazil. An abandoned private oncology clinic. The building had been empty for several years. The clinic had moved. The equipment was hastily abandoned, including a teletherapy device for tumor treatment. Inside is a capsule containing cesium-137 chloride. Two men enter the building and see a metal apparatus of the same name. They decide to sell the scrap metal. They take it away and dismantle it. Inside is something that glows blue in the dark. Beautiful. They take it home and show it to neighbors and relatives. One rubs the glowing powder on his skin. Children play with pieces of the substance. Few days later, nausea and hair loss occur. Doctors initially mistake it for food poisoning. 2 weeks later, 4 people are dead. 249 received significant doses of radiation. Several houses are demolished. The soil is removed as radioactive waste. The accident in Guyana. According to the International Agency for Nuclear Safety, IAEA, it is classified as level 5 out of 7 possible. One of the most serious peacetime radiation incidents in history. The direct cause was abandoned medical equipment, but there is a broader problem behind it. Thousands of medical, industrial, and research sources of ionizing radiation are scattered around the world, some of which are poorly accounted for and monitored. This is directly related to radium. Old medical sources based on radioactive 226, those used in oncology until the 1960s and 1970s, are scattered around the globe. Forgotten ampoules of radium are periodically discovered in various countries, in old hospital basements, abandoned laboratories, and in the private homes of deceased doctors. The IAEA maintains a database of such incidents. Unfortunately, the numbers are not reassuring. Incidentally, after Marie's death in 1934, her daughter Irene, whom we mentioned at the beginning of the video, continued her work at the same institute. René Joliot-Curie was also a Nobel laureate in 1935, together with her husband Frédéric Joliot, for the discovery of artificial radioactivity and the proof that radioactive isotopes can be created artificially by bombarding stable elements with alpha particles. But the scale of this discovery is difficult to overestimate. Until 1934, radioactive isotopes could only be found in nature. Afterward, they could be created in the required quantities and with the required properties. It was from this discovery that modern nuclear medicine, isotope diagnostics, controlled source brachytherapy, and targeted nuclide therapy arose. Irene Joliot-Curie died at the age of 58 from leuemia in 1956. Radiation. Same cause, same mechanism. Second generation in the same family. 3 Nobel Prizes in the Curie family. Marie 2, Irene 1. And 2 deaths from the effects of radiation. Pierre Curie died in a car accident in 1906 sometimes. I wonder if he would have died the same way as Maria and Irene if it hadn't been for that horse and carriage on the Parisian street. Most likely, yes. He worked with the same chemicals under the same conditions. I want to talk a little more about radon because most people don't think about it at all, but they should. Radon is a direct decay product of sulfide. It's a colorless, odorless, radioactive gas. It's continuously emitted from any rock containing uranium, that is, from virtually any rock, just in varying quantities. Granite emits especially large amounts. Radon is heavier than air. It flows downwards, accumulating in basements, underground garages, and the lower floors of poorly ventilated buildings, especially in winter when the windows are closed. According to the World Health Organization, radon is the second leading cause of lung cancer after smoking in a number of developed countries. Not third, not fifth, second. It is an epidemiologically established fact, confirmed by studies in several countries. Finland, Sweden, Ireland, parts of the UK, the mountainous regions of Central Europe, and regions with granite rocks have elevated natural radon level cells. In some Finnish homes, indoor radon levels exceed recommended limit by tens of times. This is a solvable problem. Basement ventilation, special foundation, waterproofing, and supply and exhaust systems are all effective. Many countries now require radon measurements when purchasing real estate. If you live in a house with a granite basement, this is a good reason to have it measured. Just keep this in mind. Marie Curie worked in a room without ventilation, as we mentioned at the beginning, where radon from her preparations accumulated freely. Workers in New Jersey breathed air saturated with radon from heated radium paint. Neither side knew about this aspect of the danger. Now that we know, that's something. In 2013, the U.S. Food and Drug Administration approved a drug under the trade name Rubirulishifigu. The active ingredient is Radium-223, a synthetic isotope with a half-life of 11 days. It is used for metastatic prostate cancer, specifically bone metastases. Tumor cells settle in the bones, causing pain and destroying bone structure. Zafigu exploits the same property of radium that killed the workers in New Jersey. It chemically mimics calcium and accumulates in the bones. Only now it works for the patient. Radium-223 goes to the site of metastases into tissue with active bone remodeling and irradiates tumor cells with alpha particles. The short range of alpha particles means a highly targeted effect. Tumor cells receive a high dose, while nearby healthy bone marrow is significantly less affected. Phase 3 clinical trials showed a significant increase in overall survival in patients with this diagnosis compared to placebo. The drug has been approved by the European Medicines Agency and is now used in oncology clinics around the world. A property that used to kill now heals. It's literally the same chemistry, the same mechanism of accumulation of bone, the same alpha radiation. It's just that an isotope with a short half-life was chosen. The dose is calculated and delivery is controlled. If you have loved ones who have faced this diagnosis, they may have been prescribed this drug. It's worth knowing. Radium has another role that's rarely discussed. It concerns the ocean. Radium has 4 isotopes with very different half-lives. Radium-226 to 1600 years. Radium-228 to 5.5 years. Radium-224 3.5 days. Radium-223 11 days. 4 isotopes. 4 different clockwork mechanisms. All are present in seawater in trace amounts ranging from 5 to 20 picograms per liter. A picogram is 1/trillionth of a gram. Measuring this has only become possible with the advent of high-resolution mass spectrometry in recent decades. Oceanographers use the ratio of these isotopes like a set of clocks with different rates. Ocean floor water contains more radium than surface water because radium is released from marine sediments. As this deep water rises and mixes with surface water, the ratio of the sediments changes predictably. By measuring this at different points and depths, scientists can reconstruct the speed and direction of water mass movement. Understanding how water moves in the ocean is directly related to understanding climate, how heat is distributed between the ocean and the atmosphere, and how nutrients that support marine ecosystems are transported. Radium isotopes are one of the few tools that can measure these characteristics in real-world open ocean conditions. In major international oceanographic expeditions over the past 20 years, collecting samples for radium isotope analysis has become standard procedure. Along with temperature, salinity, and oxygen content, This element, which most people only know a few words about, glows and is dangerous, is proving to one of the keys to understanding how the ocean works. There's a question I want to ask you directly, not rhetorically, but for real. What are we currently using as thoughtlessly as people in the 1920s used radium? This question has a structure. Every time humanity has gone through a history similar to that of radium, the same pattern has emerged. A substance appears, it proves useful, production and widespread use begin. 10, 20, 30 years pass, and medical statistics begin to show signs. Science confirms the connection. Standards are introduced, practices change. Tetraethyl lead in gasoline, chlorofluorocarbons in radium. One pattern. Slowly, because long-term consequences require long-term observations. This is the shortcoming of science. This is its integrity. You can't say something is harmful until you have data. But while data accumulates, people live and work in conditions that will later prove dangerous. I don't know what exactly the radium of our time will be. No one does. If they did, they would have banned it long ago. By definition, it's something we don't yet know enough about. But the very existence of this pattern is a reason to approach new substances and technologies with reasonable caution, neither with panic nor with a rejection of progress, but with caution, with willingness to reconsider our judgments as new data emerges. This, in essence, is the scientific approach. The same one Marie Curie applied to chemistry, only now to our own practices. Marie Curie changed the understanding of matter, discovered 2 elements, coined the word radioactivity, wrote textbooks, trained students, founded an institute, and received two Nobel Prizes for her work in an era when it was almost physically inaccessible to women. She made the method for isolating radium publicly available and was left without the funds to continue her research. And her notebook, which she held in her hands every day, will continue to radiate for several millennia. Radium is unforgiving, but that's precisely why it had to be learned. And it was through this learning, through deaths, through trials, through avoidable tragedies, that humanity understood something important about the nature of radioactivity, about the structure of the atom, about the limits of permissible exposure to living tissue. This knowledge was costly, very costly, but it exists, and it works in oncology clinics, on oceanographic expeditions, in radiation monitoring systems, in regulations protecting workers. This is no consolation for those who paid the price, but it is an honest conclusion. Friends, if something in today's video struck a chord with you, let me know in the comments. I'm especially curious if you knew about the Radium Girls before this video, and that Curie's notebook is still in a lid container. Did you know about a porter a day from Great Bear Lake? I try to read and respond to all your comments. Thank you for your feedback and for choosing our channel. See you on Fool's Gold, the channel where we take the periodic table and find stories that don't fit into any textbook, but which actually happened. See you soon.